Welcome, this is Dr. Hisham Saeed. In this lesson, we'll learn about stochastic scheduling and range estimating, or what we call the PERT method. This will be based on what we learned before about cost estimating and scheduling, but we will revisit these two topics knowing that there is something called probabilistic, or the idea is we're not certain about anything in life, right? So far we did have assumed we have accurate estimates of productivity rates and cost estimates. So what we call crisp estimate. It's just one number. What's the cost of this activity? It's $5,100. But is this a valid assumption? So this is a valid assumption if you're really certain about what you're doing. So it's for projects that cookie cutter projects with very controlled environment. You've done it 100 times before and you know that it will cost you this. But this assumption is not valid for all projects, especially complicated ones. So planning under uncertainty, this is what we're talking about here. There is uncertainty and you're not certain, you cannot commit to a crisp value of either duration or cost estimate. So planning under uncertainty is what we call stochastic planning. And in this lesson here, we'll learn about stochastic scheduling and stochastic cost estimating, or what we call range estimating. So that's based on one thing that we're certain about, is that all planning has some uncertainty to it, and it's up to you to acknowledge that or not. So it's a decision that you make when you develop the plan of a project. So for probabilistic scheduling or stochastic scheduling, there are multiple ways you can handle probability or uncertainty. The first one is simulations. So you can use computer to do many trials and many simulation iterations or trials of the project. Every simulation trial, you change the values of your durations or cost estimate, or here we're talking scheduling, so you change the duration of different activities. You do CPM calculations, you get a different number for project duration, and then this will be the sample. Like all these trials will be the sample, and you can do statistical analysis and probabilistic modeling to that. This is one method. Or the other one is using probability to model and probability principles to model the duration of the activities and the project duration. So for our case here, we'll use probabilistic, or in this case it's based on statistics, but we'll use here what the method called PERT. So PERT stands for Program Evaluation Review Technique. I'm not sure why they call it this way, but those who develop a method has the right to call it anything, so they ended up calling it PERT. So PERT here introduces uncertainty in the number that they use to estimate the activity duration. And they use that by estimating actually not one value for the duration of each activity, but three. So the optimistic value, the most likely value, and the pessimistic value. So optimistic is what will be the duration of the activity if everything went wrong. And then pessimistic duration is what's the duration of the activity is everything went perfectly, nothing negative happened. And then most likely is what you're most likely expecting to happen. And with these three estimates, you can build up a beta probability distribution for the activity duration. So the optimistic duration will be the least value, the pessimistic will be the longer, and most likely will be in the middle. And the difference between these three values will determine the skewness of the probability distribution of the activity duration. So for example, the blue one here is a PERT or beta distribution of 0, 10, 20. 0 is the optimistic value, pessimistic 20, and 10 most likely is exactly in the middle, so it's symmetrical. There's no skewness here. The red one is skewed to the left, so it's more optimistic than pessimistic. But the black one is very pessimistic. Like the most likely is pretty close to the pessimistic estimate of the duration here. So once for every activity you have the TA, TE, and TB, you will be able to represent that probability distribution by the two statistical values to represent any probability distribution, which is the mean and the variance. So you'll be able to calculate the expected mean duration, which is using this formula, kind of using weights. So you can see the TA has a weight of 1, TB has a weight of 1, TM has a weight of 4, and you divide by the sum of weights, 6. And then the variance will be the difference between TB and TA divided by the total of sum of weights, you can say 6. But remember, this is the variance is to the power 2. And we need to differentiate here very carefully between the variance and standard deviation. Of course, from basics of probability, the standard deviation is square root of the variance, or variance is sigma to the power 2, but the variance will be equal to that. Or I can say sigma, standard deviation, is equal to TB minus TE over 6. So now the process is you have 3 estimate durations for every activity. That helps you to calculate 2 values, probability values for each activity, the mean and the variance. And then the question is, now that's for the activity level. I know now how to represent the probabilistic duration for it, but what about the total project that's made up of a network of activities and the logic between them? How to come up with a probabilities distribution for the project duration. So we'll use here the central limit theorem. Maybe you learned that from your applied math class, probability intro class. But the central limit theorem here says that that the sum of large number of random variables will tend to produce a normal distribution. So the sum of these too many random variables, this sum variable will be a normally distributed variable. So how we can apply that to our case here of scheduling? So for a chain or path of successive activities, I'm not adding all activities or durations of all activities. I'm just following a chain or a path of them. The total duration and the variance of that path or chain will be as following. So the sum of the means will be equal to the mean of the sum. So meaning that the mean of the duration of the whole path will be equal to the sum of the means of the activities on the path. And then the variance of the sum, meaning that the variance of the duration of the path total duration will be equal to the sum of the variances of the activities on that path. So if I have activity 1, 2, 3, each one I have its mean and variance. The mean duration of this path or chain will equal to the sum of the mean values, and then the variance will be equal to the sum of the variances. So that's the central limit theorem. Pay attention that I'm not adding standard deviations, I'm adding the variances. So this rule applies on the variances, not the standard deviation. So once I do that, now I have a probability distribution for the path or chain of activities, not the project duration yet. So that will follow a normal distribution. And just refresh your memories about normal distributions. It's represented by the mean or the average, the mean value here, and the standard deviation is the spread of that bill shape. So here you have, if you have the mean here and add up the standard deviation positive and negative, the area or the probability now of this range of Tx minus sigma x and Tx plus sigma x is 68.3%. And we know that probability is the area under the curve here. For 95.4 probability, you have to consider a range that's 2 sigma to the right and to the left. So that please review your basics of probability here to remember what normal distribution stands for. So now you will be able to use that normal distribution to figure out now the real question here is what's the probability of finishing within a time period of the for a bunch of activities or for the whole project. So if I have a probability distribution of the duration of a chain of activities, now the question would be what's the probability or my confidence of finishing these activities within TS duration or time. So we will see how to calculate this area under the curve, but let's move forward here to another question. So the project is made up of multiple paths, so it's not only one path. So we learned how to bring the probabilistic distribution of an activity into a bunch of activities that are in a series. Now activity or a project is made up of multiple paths. So how now to calculate or have a probability distribution for the duration of the whole project? It's not by adding all the information of all the activities, because remember the duration of the project is dependent on the longest path. So you need to focus on the longest path. So the question here, which paths to consider when you say to determine the project duration. So this is a very simple example here. I have two paths. The first path here is made up of activity 1, 3, and 4, and the second one is 1, 2, and 4. There is a mean and variance for each one, but let's say I added up the mean of the first path. I ended up with 68 days, and the variance sum of the first path is 8.83. Do the same for the second path. I have these two numbers. So if I'm worried about finishing the project within 80 days, you can see the mean of both paths are below that, so I'm not that worried. But remember, there's standard deviation here. But the question here is which path is more critical? So I have to visualize that. So let's say I'm representing path A, which is having a TX or mean of 68 days. TB has a mean of 59 days. But you can see here path A has less variation, has less sigma value, so that will make the bell curve a little slim compared to the duration of path B, this one. And my goal is to finish by 80 days. So now the question turns out to be, what's the difference between the probability of both paths finishing by 80 days? So that hatched blue or pinky kind of number, probability of finishing by 80 days by finishing the activities on path B, that's the area here. And the other area under the curve, the second curve, is the probability of finishing path A by 80 days. Question is, which one has the more probability, more confidence? If you don't know the answer, look at the other side of the tail here, the other tail of that curve. Which area here is less? So I see here that the area of the pink, that the area that under the pink curve is less than the area under the blue curve. If this area is less, this means that the pink curve to the left, the area is more than the blue to the left of the 80 days. So this means that TB is more than TA. Probability of path B is more than the probability of path A finishing by 80 days. So I'm more confident about path B than path A. So that translates into path A being more critical. So that's the paradigm shift you need to make about once you deal with probability, it's not about the longest path, it's about which one is more critical or more uncertain about. So that's conceptual understanding of what's really happening here. But let's simplify things so we can do the analysis. So there are couple of assumptions we have to make here. First one is you only need to analyze one critical path or one path of the project. So we will not do this analysis we did here just for explaining the complications we deal with when we represent probability for paths. But for our case here, critical path will be determined by the mean completion times of the activities. So we'll focus on the mean times, put these on the network, do the CPM calculations using these mean durations of the activities, and then the path with the longest duration, this is the critical path. So no need to consider multiple paths of different durations or different length. We acknowledge that they have different standard deviations, but we will just focus on the mean values here. So the mean duration of the paths will be the determining factor here. The second assumption here is that the requirement for central limit theorem to work is to have so many activities, many activities to add up. But in our case, in projects, especially when you talk about path within a project, you will not find many activities, maybe 20, 30, maximum 100. So that's maybe not enough to statistically, be able to use central limit theorem, but we'll assume that that's fine in our case. All right, it's a little rough assumption, but just to be able to use this method theoretically in the course. And then the third assumption here is that we're assuming that the activities are independent random variables. So there's no impact between the probability distribution of the duration of one activity over the other, which is not the case. Like if I work by someone else, my productivity will be impacted by if they're chewing a gum. Imagine that. So imagine on a construction site what will happen. But we're assuming here that they are independent. Activity A and B, if they happen at the same time, whatever happened in A will not impact B. So that's the third assumption we have here. So the PERT process here is shown. We have 5 steps. Kind of we explained all of them. So first of all, you have for each activity come up with the 3 estimates of the durations. And then these will be used to calculate the mean and the variance of the duration. Use the mean duration of activities to calculate or do CPM calculations. And then identify the critical path or paths, because when you apply the mean durations and use CPM for these, you might end up with 2 durations or more with the same mean duration. So you still may end up with more than one critical path. But for these critical paths or path, the mean duration will be the sum of the activities on that path, which is what you do in CPM calculations. And then the variance of the path will be now you adding the variances of the activities on that path. All right, so this is something you have to do after the CPM calculations here. So now you have the mean value and the variance value of the project overall duration. The next and the last step here is to use the Z tables to find out the probability of finishing the project by a specific deadline. And that's the real question to answer here. It's not what's the mean duration of the project, but it's what's the probability based on that mean duration of the project and the variance. What's the probability of finishing the project by a deadline? So question, let's see this question here. Probability of finishing a project that has a mean duration of 68 and a standard deviation of 8.83. We're finishing that by 80 days. So if I represent the normal distribution of this project, it's 68 with spread of the bell shape based on the sigma equal to 8.83, and my deadline here is 80 days. So how to calculate the probability under the curve here, which is the probability that t is less than or equal to 80, or being able to finish by this deadline. So what I will do is I will normalize the normal distribution into a z distribution. And my question, instead of finding what's the probability of t less than or equal to 80, will be what's the probability of the z variable, or the z, it will be less than or equal to a specific value corresponding to the 80 days deadline. How to find this z value is by the z formula here. Very simple formula. So a z for any value in the normal distribution will be equal to this value in the normal distribution minus the mean divided by the sigma. So The value I'm interested in is the deadline, 80. So 80 minus the mean 68 divided by the standard deviation 8.83. That will mean that z that corresponds to my deadline is 1.63. This is why we ended up here with 1.63. Of course, the z value that corresponds to the mean is 0, right? So that's the point. Normalizing here means that the mean of the distribution here is not a variable or a value that is a duration value. It's actually now equal to 0, and that will simplify the way we calculate the area under the curve, because normal distribution is pretty useful representing natural phenomena, but it's very hard to deal with it statistically and mathematically. So we're simplifying or transforming it into a z distribution, which we have easier ways of dealing with calculating its probabilities. So we'll use the z table here. So the z table, I end up here all the way to the question here. What's the probability that z will be less than or equal to 1.63? So how to get this value here? So the z value is broken down into this column here and this row. So 1.63 is read this way, 1.6 and then 3. Confusing, right? But if I look at this number here, that corresponds to 0.53z. So this is the way to read it. This column here is giving you the two digits, the first two digits of the value, and then this row here is giving you the third digit of the value. So 1.63 is read as 1.63. Now you will match these two values with the element in the table. This element is the probability of z less than 1.63, which from here it's a decimal value, but I can write it in a probability, a percent value. So it will equal to 94.84. So that's basically the answer. The answer to this question of finishing the project by 80 days is that there is a probability of 94.84 finishing the project by 80 days. It's pretty good. Like, I have less than 5% probability of not finishing by 80 days. So we will see a full application of PERT in this example here. Different parts, different scenarios. We're given for every activity the sequencing logic, or what each activity depends on, and the three duration estimates, the optimistic, most likely, and pessimistic durations. Just to get you started on that, we'll solve that in the class. But to get you started, this is the calculation for the expected duration and the variance from the expected duration and the variance formulas for the beta distribution. So I did this actually in Excel. I didn't have to calculate it one by one, but this is a good start for you until we meet in class and solve or complete the solution of this exercise. So we finished the major part of this lesson, which is stochastic scheduling. We'll apply the same principle in estimating, which we call here now, instead of stochastic estimate, it's called range estimate. So it's very similar to PERT application in scheduling. The idea is to be able to consider uncertainty in project cost estimates. So these are the steps, and it's much easier than stochastic scheduling to do apply PERT in cost estimating. So first of all, you have to make the 3-point estimate for the cost of each activity or each line item in your bid. So you have the lowest estimate, most likely, and highest estimate. Then the next would be to calculate the expected cost estimate and variance for each activity using the similar formulas we've seen before. And remember, in stochastic scheduling, we used to do CPM calculations to find the project duration, to find the longest path. This is in time. In scheduling, we are dependent on the longest path. But in cost estimates, the total project cost is the sum of all activities, not only the critical activities. So, and that makes our life much easier. You just add up everything. So you add up the estimate, the the expected cost estimate for all the activities. That will give you the expected cost estimate for the whole project. You'll add up the variance of all activities. You end up with the variance of the cost estimate for the whole project. And these two values will be your input into the Z table analysis to figure out or to answer any probability questions. What will be the probability of having the project cost less than this budget? Or what's the probability of having a cost overrun when I have my budget is this? So there are many questions, probability questions you can answer once you end up with the EX and VX, the expected and the variance values for the project total cost. So another example we'll see in class, how to deal with range estimating. It's the same principles we applied in scheduling, but in much simpler way because we're not dealing with CPM calculations. So that's it for this lesson. Thanks for watching, and I'll see you in class. Take care.